Now this one will be short because I'm just going over the homework. And hi, this will be a very short video. I'm just going to go over the answers to homework 4. And so we'll start with the true-false questions. Now before we start, before you read this, look at this video, I would suggest you go to the website and click on the answers to homework 4 and print that out and have that in front of you while we go over this. All right, now that you have that in front of you, let's look at the true-false questions. A, every language accepted by an NFA is accepted by some DFA. Yes, that's true. Every language accepted by an NPDA is accepted by some DPDA. That's false because we've learned that deterministic push-down automata are not equivalent to non-deterministic. Well, actually, every deterministic could be made equivalent to a non-deterministic, but not vice versa. All right, now the third question, C, every language accepted by a non-deterministic Turing machine is accepted by a Turing machine. Now that's true. And let's see if I can explain why that's true. If I have a Turing machine and I put in a string here, and then I put in G, which is a guide string. Now, a guide string would be a sequence of instructions. Now, while the Turing machine is executing, all right, let's say we have a non-deterministic machine M, a non-deterministic Turing machine, and a guide string is we can think of it as a Boolean because we can assume that M has no more than 2 choices at every step. If you try to think of a labyrinth, how would you escape from the labyrinth? You would have a string connecting where you are to the entrance. Perhaps when you wandered in, you left the string behind and then you rolled it back up as you left. Now, in this case, the guide string tells you what choice to make. So you emulate the non-deterministic computation of M, but you make it deterministic by using this. Like, for example, 0 might mean take the first step whenever you get to, take the first choice when you get to the first step, take the second choice at the second step, the first choice at the third and fourth steps, and so forth. That turns it into deterministic. Now, that means that I can emulate this by a non-deterministic machine which stores the guide string. All right, now, the class of Turing machines which allow movement of the head, the head to not move during a step is equivalent to the class of Turing machines which require that the head move at each step. And that's true. We can emulate not moving by making 2 moves, one to the right followed by one to the left. And that is effectively a not moving. All right. The class of PDAs which accept by final state is equivalent to the class of PDAs which accept by empty stack. Well, that's true. There must be a simple explanation of that, but I can't think of it exactly right now, except that, well, maybe I'll come back to that one. The class of 2 PDAs, that is automata with 2 stacks, is equivalent to the class of PDAs with 1 stack. This is false. In fact, 2 PDAs are Turing power. They're equivalent to the class of Turing machines. Because with 2 stacks, you can emulate a Turing machine. when you have two stacks here, you can emulate the tape going up one stack and down the other. You see, up this way and then down that way, and you can roll back and forth by popping this and pushing it here, or vice versa, pop that, push there, so you can effectively move along the tape by popping and pushing stacks. The class of C++ programs is equivalent to the class of Turing machines. Well, yes, you can emulate a Turing machine using a C++ program using linked lists. Now, the infinite tape is equivalent to the semi-infinite tape. That's H. The answer is true because you could simply fold the tape. If you have an infinite tape here, infinite in both directions, you can cut it and simply fold it this way, and you know, A, B, C here, D, E, F, so you have A, B, C, D, E, F, and so you can effectively make it a single a semi-infinite tape, but with two symbols at every cell. All right, now the complement of any recursive language is recursive. That's true. If you can decide that a string is in the language, then you are also deciding that a string is not in the language, whether it is not in the language. All right, the complement of an RE language is RE. That's false. For example, the halting problem is recursively enumerable, but its complement is not. Another example would be the diagonal language. The diagonal language is not recursively enumerable, but its complement is recursively enumerable. All right, now let's look at problems on the rest of these. Prove that a language L is recursive, if and only if there's a machine which enumerates L in canonical order. I've actually done a tape on that already, and so I would suggest you go and look at that one. So we'll skip that. And the last question also is to prove that the halting problem is undecidable, and I printed that out here, but I did that one on the same tape as the other, so I don't do it again. Now let's look at problem 3. All right, and we're now looking at the following question. Look at this language L. Can we find a general grammar, mainly an unrestricted grammar, which generates the language? It's all strings of A's that have square length, like 0 squared, 1 squared, 2 squared. All right, let's look at this grammar here. Let me tell you briefly. First of all, I gave some examples down here. So take a look at these examples. In the first example, I generate just the empty string. That's done just very simply. I needed a special production for that one. Now, to generate just one A, I went through a sequence of derivations here. Derivation, and then to generate 2 A's, or actually it would be 4 A's, I needed 4 lines to write the derivation. But there must be some sort of philosophy in here. Now the one that generates 9 lines is right here, but I left out a lot of steps because otherwise it would be, you know, a big number of lines here. What's the basic idea? Well, F stands for left. I didn't use L because L is the name of the language. R stands for right. So these are the left and right bookends. Little a, well, what is little a? Well, see, I generate a little a by reversing capital A and capital B. Now we can think of A as being a generator that generates little a's by passing over little b's. I'm big B's. And the way that happens, it happens here. Now if you look at these, you will see that for a large number of steps, I'm executing this. I'm taking capital A, capital B, and changing it to little a, capital B, capital A. So the capital A moves to the right, and each time it crosses a B, it generates a little a. When it reaches the right bookend, it is destroyed. And this can happen any number of times. So the first time, when you first run this, you get a single A and then it's destroyed. But then when you initialize this again, when you generate another A, you generate 2 additional B's. That means that the next time you run through it, you generate 3 A's. So the first time through, you generate 1 A. The next time, it generates 3 A's. Now that makes 4. And then the next time through, you generate 5 A's. And then that sum is 9, which is the next square. But at some point, you stop generating A's. Instead, you change the last bookend into D, which is the destructor. And when D hits an A, it ignores it. And when D hits a B, it destroys it. Because the little a's you want to keep. And the big B's you want to destroy. Now, in the output, you'll notice, if perhaps you weren't able to print color, but if you were, you would notice that certain of the sentential forms are in red. And let's see here. One of them is this. That has 1 A and how many A's and how many B's? It has 1 A and 1 B. The next one that I'm talking about doesn't occur in the second derivation, it occurs in the third derivation. And this one is F, A, B, B, F, A, B, A, B, A, R. Now this sentential form has 4 A's and 3 B's. No, there's a B here. All right, no. That has 4 A's and 3 B's, and this is 4 here and 3 there. Now when we do the next derivation, which has many, many lines, and I didn't write the whole thing, we're going to have at some point 5 B's and 9 A's. And that, of course, is shown here with a lot of dots in there. And eventually, when the B's are all destroyed, you just simply get 9 A's. On page 4 of the homework answer sheet, I bring up the fallacious contradiction. You might call that the unicorn fallacy. And here it goes. You consider these 2 statements. Every unicorn has a horn. Now that has to be true because that's part of the definition of a unicorn. All right, now it says no unicorn has a horn. That's also true because you can't find a unicorn that has a horn. So you look at this and it says every unicorn has a horn and no unicorn has a horn. That sounds like a contradiction. But is it a contradiction? And the answer is no, it's not. Because there's no unicorn. And therefore that's not a contradiction. Both statements are true. They don't contradict each other. Now this is important because when we prove the halting problem is undecidable, we reach a similar situation. We're going to say that this Turing machine description is a member of the we're going to prove two things: that it's a member of the halting language and that it's not. Now that looks like a contradiction, but the way we resolve this is just like the unicorns. This is the unicorn. It does not exist. And since it does not exist, these two statements are both meaningless and hence don't contradict each other.